Okay, so let's take a look at the central limit theorem. So first, some math. The central limit theorem says that x bar, or the sum of x divided by n, that no matter what the distribution of the individual x's, that x bar will be normally distributed. Okay, so let me show this. Okay, so here I'm going to find the expected value of x bar. Okay, this goes back to our expected value steps. Here I've got a constant of 1 over n. I'm going to bring that out, and I get the expected value of many different x's. Okay, so I bring that expected value inside those brackets like so. Here you can see the expected value of any x is called mu. I'll just replace the expected value of any of these x's with mu. How many of them do I have? Again, you can see that there are n amount of them. So I've got mu n times. This n cancels that n, and I'm left with the expected value of x bar is just equal to mu. I can find the variance of x bar just about as easily. Again, I'm talking about the variance of this formula. The coefficient here is 1 over n, so if I'm going to take that out of a variance, then I need to square it. So this is 1 over n squared. And then I just have the variance of x repeated n amount of times. Notice here that the variance of any particular x, so x1 or x2, is always sigma squared. Okay, so this is just n amount of sigma squareds. I've got an n on the numerator, I've got two n's on the denominator. I can cancel out one of the n's and one of the n's, and I'm left with the variance of x bar is sigma squared divided by n. Of course, then the standard deviation of x bar is just the square root of the variance of x bar. Here's the variance of x bar, I take the square root of it. And the standard deviation of x bar then is sigma divided by root n. What this means is that here I can, in our old z formula, I used to have x subtract mean divided by the standard deviation. So now I've got x bar minus the expected value of x, which we've shown is mu. Okay, so here we've shown it's mu. And then we're going to divide by the standard deviation of x bar. Used to just be sigma, but now we've seen that the standard deviation of x bar is, of course, sigma divided by root n. Okay, so we can write it this way if we're talking about averages. We could also write it this way if we're just talking about the sum of x. Okay, so here this is mathematically equivalent. These two statements are mathematically the same. What this means is that x bar, no matter what x is, what distribution x is, x bar will be approximately normally distributed with a mean of mu and with a standard deviation of sigma divided by root n. Okay, so here this only starts to do a good job really when n is larger than or equal to 25. Some textbooks say when n is larger than or equal to 30. When n gets large, x bar, the shape of x bar will become normal. Okay, so what this means functionally is there are two scales going. Just like before, we had an x scale and a z scale. Now instead of an x scale, we've got an x bar scale. We're not talking about just x, we're talking about the average of x. Okay, the middle is mu. That's where it's centered. And of course, as a z-score, mu will just be 0. Any other x can be converted into a z-score by using this formula. Okay, so x bar, whatever it is, subtract the middle, divide by the standard deviation over square root of n. Okay, so no matter what, you can transform an x bar into a z-score. Just as we transformed x's into z's. There's just a little bit of a difference. Instead of x, it's x bar. Instead of dividing by sigma, we divide by sigma over root n. Okay, so that's the only difference. And then you can convert any x bar into a z-score.